done a very good job. He has invited experts from various parts of the country, and they'll be covering different aspects of the malware. So I thought that I would be doing something which was not in the list of the topics which were given to me. So this was part of a course where we were preparing for ISA, Information Security Education Awareness Project. And the topic that I'm going to deal with today is known as anti-analysis techniques that malware writers use to ensure that analysts, defenders, cyber defenders, they cannot detect what the malware is actually doing. So basically, there are many different techniques, but I'll be concentrating more on code obfuscation techniques. So in case of a malware, anti-analysis and anti-analysis terms are quite common. Anti-analysis terms are the anti-analysis techniques are the techniques which are to defeat analysis, and generally it will be employed by malware writer. Anti-analysis techniques will be developed by defenders who want to detect malware and remove it from the system. And these are the analysts that have to ensure that if malware is employing any anti-analysis techniques, they can mitigate that, counteract that, and still detect the malware. So if we look at anti-analysis techniques, an overview of this, generally malware writers will be using encryption. This is very widely used technique. And then compression, polymorphism or metamorphism, and code obfuscation. Now, encryption has a problem that there has to be a key which can detect which can be used for decryption, and malware writer has to provide a mechanism of ensuring that this key or the correct key is actually delivered to the malware. And another problem with the encryption is that most of the analysis systems can detect that this data is encrypted, and they may or may not allow a binary to run if it is having too much encryption or a compressed data. So as a result, these encryption itself can raise a red flag, and therefore malware writer may have to go for something more innovative to ensure that their malware gets run and at the same time it is not detected. So obfuscation is one of the solutions. And naturally, the person who is trying to detect malware has to also depend upon many tools, and the tools in the arsenal are debuggers, virtual machine environments, emulators, and then they will also try to do some kind of dumping the code in the malware. So when the malware is going to run, it is going to have its presence in the main memory. So dump that code and try to then analyze what is happening. So now malware writers have to take some methods to ensure that this forensics of the malware cannot be done. So they need to develop some anti-debugging strategies, anti-VM strategies, or anti-dumping strategies. Then I already said that they can go for metamorphism or polymorphism. Metamorphism is generally that you are trying to implement the same code functionality by writing different kind of code. And polymorphism is also similar. So they are similar in the nature, but the way they are actually implemented is different. Anyhow, I'm not going to concentrate uh, efforts there, but code obfuscation technique itself will also be used for generating different polymorphic or metamorphic variants. Then nowadays, malware writers are using what we call fileless malware. Generally, when a malware comes into the system, the malware has to be stored as a file somewhere on the hard disk or some non-volatile media. And fileless malware will try to uh, ensure that none of its traces along with its own code is ever stored on the hard disk or the volatile media, sorry, non-volatile media. So So detecting the presence of such a malware becomes very, very challenging. So why malware writers have to use these techniques? Answer is very simple. They want their malware to run, and they do not want anyone to be aware of the presence of the malware for as long as possible. So the longer a malware remains undetected in the system, the larger are the benefits for the malware writer. So the malware writer can actually extract the data for as long as possible. So generally, it will be using some kind of stealth techniques. For example, a file which is not easily visible. So that is by changing the hidden attribute. But basically, this can be hidden from the human eye. But system can know that yes, file is still there. So this is not a very, very, very effective mechanism. And then it could be actually malware can be broken into multiple parts, and or malware can so initial the first part of the malware can actually download the second part of the malware from somewhere. So there can be different strategies that can be used here. Now generally when a malware is going to detect whether it is being analyzed or not, then it has to be aware of which antivirus is going to create, what will be the name of the process associated with a particular antivirus. So malware will first of all check in the list of the processes whether that antivirus is running or not. If the antivirus is running, then malware might not show its evil face. It can show itself as it can pose itself as a very benign file by not at all running the malicious script execution. Malware can also, now most of the antivirus solutions are cloud-based. So malware can also monitor network access and try to see whether there is an access available to a website where the antivirus solutions are being hosted. Generally, malware will try to change the configuration of the data which is stored in the registry file to bypass the security mechanism of some of the apps, for example, Word, Excel, etc. Or malware itself can hide its code in the Windows registry. So all these mechanisms can be used to ensure that malware remains beyond the reach of any antivirus software. And then we already talked about fileless malware, which is difficult to detect because it leaves very low footprint, because it is not going to make any entry into the log file. It is not going to make any entry into any of the files on the hard disk. So it becomes very difficult to detect the presence of such a malware. So generally now, I think you must have done some initial session today, and you know that malware can be analyzed either through static methods or dynamic methods. So in static methods, the malware is not at all executed, just the code of the malware is analyzed. Now naturally the code of the malware is not in a source high level language, it is a binary data. So the people who are going to analyze this binary data, they are aware of the format of the file, which will be an executable or a script file. So they are aware of the format and they try to decompile this file or disassemble this file to understand what it is. So now naturally the very first tool in static analysis will be disassembler. Now the problem is disassembler is also a program or a software which is which is based on certain algorithm or some logic. So now malware writers, they will try to change the binary code in such a manner that this disassembler is not able to work properly, and it tries to give an outcome which is actually different from the original program. And this is generally done by making the disassembler jump in the middle of an instruction, or by adding certain bytes which are confusing. So they try to prefix some data by a byte which make a data appear as an instruction, or which make an instruction appear as a data. I'm sorry about these peacocks. I'm really sorry. So the point is that everything in the binary is in binary, whether it's data or whether an instruction. And in case of Intel-based systems, code and data and instructions, code and data are intermixed. So if even with a 1 byte offset, the entire program can be misinterpreted by something, misinterpreted as something completely altogether different. And that's what the anti-debugging techniques try to, anti-debugger or anti-disassembler technique they try to do. So the idea is that disassembler or decompiler, these software are not able to uh, parse the binary properly and give an output which is completely different from the actual malicious program. To make it more difficult for humans to understand, of course, unnecessary code is added. Library function is actually replaced by what we call an ordinal number, which is a kind of index into the table of the library functions. Entry point is obfuscated by using too many jumps here and there. So there is a jump instruction, it takes you somewhere else, then there's another jump instruction, takes you back. So by going through multiple jump instruction and using garbage byte instruction, the disassembler may not be able to align properly with the instructions, with the actual instructions in the program, and can give you a garbage output. Now, malware writers are also smart. So generally, they also use what we call, here in this particular case, this is a common code, then this code becomes changed, then this code gets changed, then this code gets changed. What they do is, this code does not look like a code for assembly language of Intel processor, because it is not meant for that. So basically this is meant for a virtual processor or a hypothetical process for which ISA is completely different. Instruction set architecture is completely different. Now, so this is a kind of code which will run in that hypothetical processor. And then there is what we call an engine, which will make sure that this code is correctly interpreted when it is being run on Intel microprocessor. So a kind of micro virtual machine is inserted into the code. And there can be multiple such virtual machines. And the advantage of using these virtual machines is that uh, when the new version of the malware comes, the machine may be changed. So, this customized virtual machine, or making use of interpreter, allows them to use a customized instruction set architecture on a hypothetical processor. And at the same time, this may or may not be generating entropy which is significantly different from that of a binary, and hence entropy based detection of whether this is encrypted content or whether this is a compressed content will not work here. Now, in case of a dynamic analysis, the malware is executed on a machine, but because the nature of the malware is not known, most of the analysts, they will run it on a virtual machine or a emulator. And the malware will try to detect whether it is running in a virtual machine or an emulator. So naturally, when a virtual machine is run, virtual machine is also a process which is running on the host excuse me, host operating system. So malware can check whether this process is running or not, or malware can use another technique which is known as time analysis. So what the malware will try to do, it will execute a code which will be typically a loop of certain number of iteration, and then it will check what time before the loop was executed and what was the time after the loop was executed. And actually then it will look at the difference between the time. Now on a physical machine, if there is no emulation or there is no virtual machine, it will be much faster. So naturally, if it is running on a slower machine, because of the interpreter required for interpretation required for virtualized environment or emulated environment, it will take more time. So by looking at this time difference, the malware is able to know that it is running on a physical machine or it is running on a emulated machine. It can also use various other mechanisms to check whether it is running on a physical machine. It can try to check what is the charging level of the battery, if it is being run on a smartphone or a laptop. Who is the service provider? What are the wireless networks which are available? So naturally, the emulator cannot provide all versatility which is actually present in a real environment. So these indicators may remain fixed, and as a result, malware writer will be able to know that it is running on a physical machine or not. So in this particular lecture, we'll be talking more of obfuscation. And as I said, that if you're talking about anti-disassembly or anti-decompilation approach, the main purpose of the malware writer is to defeat the disassembly or decompilation algorithm and uh, and throw them off their guard, throw them off their rails so that they do not run properly. So now the purpose in the obfuscation is that you are trying to change a code in such a manner that its structure gets changed, but its functionality remains the same. Okay. Now, if P was our original code, so after code obfuscation, P is the set of the instruction which is making the original code, and P dash is the set of the instructions which is making the obfuscated code. So P to P dash is a transformation such that both of them will have the same observable behavior. So outcome of the same of them remain the same. So if for a given input uh, P terminates, so P dash must also terminate. If P does not terminate, then P dash may or may not terminate, because it doesn't matter if the original program is not running, is not able to terminate on some particular input, which may or may not have been foreseen by the developer. So it doesn't matter if the equivalent program terminates or not. So now obfuscation is not only the tool which is used by the malware writer, it can also be used by the software developer. And the aim of that both is the same. Software developer wants to protect his or her code and do not want other people to know what this code is actually doing and how this is actually implementing a particular functionality. And it could be to ensure that undocumented processes, which might be proprietary processes, are not easily discoverable or uncoverable by other people. So the main theme in obfuscation is to uh, lower the readability of the code. Now, we do not just want that humans should not be able to read the code. We also want the machine should not be able to understand the code and analyze it. So basically, it is hardening code against the reverse engineering. Malware writer will also use it for the same purpose. They do not want their code to be analyzed and understood by the analyst, because if the analyst understands the code, how the malware was developed, they can also try to create techniques to detect the malware. Sorry, but there is a difference now the way the obfuscation will be used by software developer and malware writer. Generally, the software developer has to sell their code, sell their product, and their product has to be efficient in terms of space as well as time. So it should not, so they cannot insert too many uh, dummy code or unnecessary code to make it lengthy or complicated, because then the code performance will go down. But malware writer do not have any such restrictions, so they can add unnecessary code to make dynamic analysis difficult or even static analysis difficult by making too many jumps here and there, adding code which does not make any sense or which is just for confusing. Sorry. But software developer cannot use it for the same purpose. Now, how do we know whether the obfuscation is very good or not? So there are two parameters by which we can try to see whether it is good or not. One is potency, another is resilience. Potency is indicative of how effective obfuscation is to impact readability by a human observer. So it affects the human readability. More unreadable the code is from human perspective, it is highly potent. Resilience is basically how effective it is against de-obfuscation measures. So basically, we are talking about how effective it is against any machine on which a de-obfuscation algorithm is run. Transformation could be so when we are doing obfuscation, we are basically transforming code from we are basically transforming the code, and this transformation can actually change the layout of the program, or it can change the control flow of the program, or it can change the way the data that is part of the program is arranged, and then there could be some other preventive transformations. Now, we'll be talking about layout transformations, control flow transformations, data transformations, preventive transformations. If you look at the control flow transformation, some of the names are quite similar to what a compiler optimization does: inlining and outlining, branch insertion, loop transformations, flattening of control flow graph. So we'll be talking about this now. So yes, optimization of compiler, the way the compiler optimizes the code actually preserves its functionality, but it changes its syntax. Semantics remains the same, but the syntax or the organization of the instruction which are making the program changes. The first that we are going to discuss would be layout transformation. Sorry. Layout transformation, we are changing the format of the code. So one way to do it is remove indentation. Now, this may be possible in some of the languages like C. Python may or may not permit it. In fact, most of the modern Python compilers and interpreters, they do not allow you to change the indentation as per your whims. But if you look at C and C++, you can change the indentation. The change of indentation basically affects human readability. As far as the machines are concerned, machine readability is not at all affected. So comments can be removed, indentation can be removed. Then instead of putting each line, one line, line of code on one line, we can put multiple statements of the code on the same line. Again, it will impact the readability. Change the name of the identifier. So instead of writing, for example, if I write a program integer x comma y, z equal to x into y, return z. This is not as readable as if I say write integer width comma height, area equal to height into width. Of course, my variables are not uh, too different, difficult to read. But what if I use variable like x, x1, x, x, xl? So now the program readability starts getting affected. So by changing the name of the variables, changing the name of the functions, the program can be made very, very difficult to read from human perspective. Now, even if you actually try to analyze this program through machine also would require some kind of help in to make it human readable to find out which variable should be replaced by which string. So naturally, if I use variables like this, it becomes difficult, very, very difficult to understand the program flow. especially if these strings are very large. So through these layout transformation, they affect human readability. Deobfuscation is not very difficult because machine readability is not affected. So potency is not very, potency will depend upon how the variable names are scrambled, but resilience is not very high in this particular case. To increase the potency, program length can be increased. So one way to change the program length could be that instead of going for modular program, where the program is divided into functions, we can have a monolithic program, one single program which with no division between function. Now dividing into function makes it easier for us to understand what the program is doing, because if we understand what function 1 is doing, what function 2 is doing, what function 3 is doing, it is not very difficult to understand what the program is doing. So by increasing program length, by adding unnecessary code, or by making a single module, by removing all other functions, we can make it difficult to understand. Then we'll be talking about this later on. Then more classes and methods can be introduced. Number of nested loops can be increased. Number of nested if as constructs can be increased. And data structure can be rearranged in a different way. So instead of using a scalar, we can use an array. For if I use integer x3 rather than saying integer length, width, height. So integer length, width, height. If I'm saying that xxx0 is representing length, xxx1 is representing width, xxx2 is representing height. So here the developer knows what he's doing, but the person who has to interpret this program, understand this program, may not know what exactly is happening. So all these methods can be used to change potency. Now we'll be coming to it later on. First of all, let's talk about, okay. So basically what we are trying to do here is resilience, since we are making it difficult even for machine to understand what the code is doing. So if we are now, if you have read a bit of compiler theory, you must be knowing what a basic block is. So if you look at your program will consist of jump statement, or it will consist of go-to statement. Now you might not have written that go-to statement, but if you look at a loop is executing, and then it checks the condition, and according to the condition, it again goes back to either the first instruction of the loop, or it exits the last instruction of the loop and go to the next instruction. So a loop is a kind of a basic block. So a basic block is a block in which control comes to the first instruction of the block, and then it leaves the next instruction of the block to go to another basic block. So local transformation, they are applied at the basic block level, so they will be affecting a basic block. Global transformation will be applied to entire control flow graph. So we are looking at a path which can consist of multiple basic block, and then try to apply the transformation there. Interprocedural transformations, they will actually change the way the information is flowing between different procedures. And then there could be interprocess transformation. There are two different programs which are running, or two different threads which are running, and then you are applying the transformation in the way the data is being exchanged between these processes. Sorry. So now let's come to control flow transformations. Okay, so now here, this is a control flow graph. So this is a code, and this code consists of a control construct. If this condition is true, do this, otherwise do this. And we can represent this in the form of a graph. Okay, so I'm showing this graph as individual instructions. So sum equal to part 1 plus part 2. Then we are checking whether sum is greater than threshold. If it is true, then this instruction will be executed. If it is false, this instruction will be executed. So irrespective of whether this instruction is executed or this instruction is executed, ultimately we will be executing this instruction. Now here it is not exactly shown as a basic block, but if you look at this particular instruction, this is a kind of basic block. The control is coming here and then going there. Now these two instructions can be combined together into one basic block. Okay, so here the control is entering into this instruction and then leaves this instruction either to go to this basic block or to this basic block. So basically, this is a control flow graph is basically connecting the basic blocks of a program and how the control will go from one basic block to another basic block, under what conditions the control will go from one basic block to another basic block. Okay. Now, how can we actually obfuscate this program? So one way to obfuscating control flow program is like this. So what we are doing is we are making use of a variable, which is a kind of state. Initially, the state variable equal to 1. And then we are saying, okay, depending upon this state, what is the next set of the instruction that is to be executed? State equal to 1, it can either go to this, 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 or this. But if it is 1, it will go here, make the state equal to 2, then again go back to switch. So now the state equal to 2, so it can come to this. And depending upon the value of the x, it can either be 3 or 4. It could be 3 or 4, so it can go to different states. So now using this kind of mechanism make it difficult to understand what the program is doing. So let's say this is the, okay, so now to make it easier for us to understand. So let's say after this instruction is executed, this block is the first to be executed, then it goes back. Then let's say this block is second to be executed, and let's say again it goes back, then this can come to this block, and depending upon here, either it can go to this block or let's say this block, depending upon what is the condition here. Is that right? Now here maybe we can make sense of what this program is doing, but ultimately if there are too many states, if we can go from let's say 1 to 100 and there are too many branches going on, it will be very difficult for us to know what is actually going on. So the code is very much jumbled, and so code is actually randomly divided into different blocks, and then these blocks are stitched together through the state variable, and in each iteration the state variable will be changed so as to ensure that the next block of the next batch of the instruction which is run is the in the correct order. So all the batches are run in the correct order by ensuring the way this variable is changed from one iteration to another iteration. So basically, if you look at here, this is the kind of what we call a dispatcher module. So construct a list of basic blocks. They are split. Some of the basic blocks are split into further. Some of the basic blocks can be merged, And then these basic blocks are given number, the way I have given them number. And then how these basic blocks have to be executed, in which order they have to be executed, it is decided by the state variable, which is B in our case. So now in control flow transformation, and generally this method will be applicable for other transformations also. So either you merge different components or you split one component into multiple components. So either you break up computation that belong together, or you merge computations which may not apparently look together. Okay. So first of all, we are going to discuss this method inlining and outlining. So let's say this is how a code is being executed. First of all, it executes function P and then it executes function Q. So naturally, if I look at from another perspective, it is as if I'm executing instruction P1 to PM and then running execution instructions Q1 to QN. Am I right? Now I can achieve the same effect by doing something like this. I can actually now make it P, R, and Q, where P, now the function P, the new function P is actually consisting of only up to PM minus 1, P1 to PM minus 1 instruction. Part of the instruction from P and part of the instruction from Q make my new module, which is R. And then Q is now, I've taken some instructions from Q. So the new P and Q are different. So new P is also P minus something, and new Q is also Q minus something. And R is now making up for the difference of the whatever I've taken from P and what I've taken from Q. Now, if I look this code and this code, to my static analyzer, they will look completely different. So even if there is a signature match here, which is signature match is P of I'm making call to P and then making call to Q, this signature match will fail in this particular case. So it will actually defeat static analysis very easily. And now we have shown it that in this particular case, the sequence of P and Q becomes sequence of P, R, and Q. Actually, I can extend it to P1, P2, P3, I can make it. Now here, the cost would be that because there is a additional function which is being run, this will actually make it slower because there is an additional overhead of function. So I told you that a software developer cannot afford this kind of technique because it will increase the time taken by the program, but malware writer can do it to obfuscate the code. There's another example of function inlining and outlining. So this is, we have a method M and we have a class M. And on this class M, we want to call a method P. Okay. So now the way we have actually created a control flow graph is like this. So if we'll check whether M is class 1. If it is class 1, then it will make call to P method of that class 1. If it is not class 1, then it will check whether it is class 2 or not. If it's class 2, then it will call the method P of the class 2. If it is not class 2, then it will make a method of class, sorry, class 3 हो जाएगा इधर. Now, if you look, the way the coder has written for all these classes, the method P is doing the same thing. But just by looking at this analysis, it may not be very apparent that the same thing is being run. This code will look very different from this code. They will not look at all same. So they will look completely different. So now by making the code look like this, the complexity of the understanding of code will be increased. So resilience of the cost of code will increase also. And when I say that all these methods are same, they may not have the same code, may have the same functionality. So class 1p method may be actually rewritten as class 2p method, but with using different instructions and different order of the instructions. Now this is another way the same functionality can be achieved by making syntactic change, which may not be easy for uh, debugger or disassembler to understand that this is actually essentially same or equivalent code. So for example, in this particular case, what we are doing, let's see. There is a class C which supports two methods, method 1 and method 2. Method 1 accepts a parameter, single parameter, and method 2 accepts two parameters. And then we are writing this code. We are creating a new object of this class, and this object is X. And here we are calling X with method 1 and passing parameter A, then X with method 2 passing parameter B and C. Now we have rewritten the same class and combined these two methods as a single method. But as to which part of the code has to be, so this part of the code is same as method 1, and this part of the code is same as method 2. And now we are passing a third parameter, V, which is telling us whether we should be invoking method 1 or method 2. So now, to ensure the same thing as earlier, we will say x dot a c p. So if v is set to p, then method 1 is going to be called. But if v is set to something else, which is q, then method 2 will be called. But again, these two classes may not appear same in the analysis, because here it appears that we are having a class with two methods, and here we are seeing that this class has only one method. And the number of parameters are also not matching. But if you look closely, you understand that no, this is actually an equivalent representation of the same method. So by using interleaving of the code and merging the method, again, obfuscation can be achieved. Any questions till now? I don't even know whether I'm continuously audible or not. Hello? Hello?
Yes, ma'am. Hello?
Am I audible?
Yes, ma'am. Hello?
Any questions? Okay. Another method is that we can clone a function. And actually, we are creating three clones of this, two clones only. This is C. We are creating two clones of this class C, C1 and C2. Okay, and now what we are doing here, class C has a method M, which is consisting of k instructions. Class C1 has a method M, again it is having k instructions, k instructions, k instruction. But these instructions may not be exactly the same instruction. They may be slightly different, but actually the functionality will remain the same. Now here, I'll explain what this means. It's a predicate which is always false, or which is a predicate which is always true. So it looks as if I'm creating a object, and if this predicate is false, then I'm creating an object of type C1, otherwise I'm creating an object of type C2. And then on this X, I'm making invoking the function M with parameter 5. And then I'm invoking and because I want to use the same thing as I'm using it here. And then I'm invoking a method M1 as Now, in this particular case, because the predicate is always false, it will always create an object of type C2. So when I'm invoking this x.m5, then actually I'm sorry. So I'm actually invoking this function only because C2 is inheriting C1. So naturally, it can also invoke the function of the parent class. So here I'm making it invoke the parent function class. And so this is actually giving me the same functionality as this one. So when I say that I can implement this method, so I can clone a function and I can make it to confuse the analyzer. If the analyzer is able to know that yes, the all these codes are going to do the same thing as this, then they know that yes, these two programs are same. But it may not be that easy because maybe functionally equivalent, but they might not be structurally or or syntactically equivalent. So I'll be stopping at this point. We will have 5 minutes break and then we'll start again. Is that okay?
Yes, ma'am. Hello.
Hello?
Yes, ma'am. We may take that break of 5 to 10 minutes, ma'am.
Yeah, sure.
Okay.